Ham radio operators that operate on the HF bands understand that the distance our signal travels is largely dictated by the angle of the radiation, or the angle that the energy leaves our antenna is reflected or bent by the ionised layers and arrives back to Earth at a far point. And quite clearly, the lower the angle, the greater the distance. It doesn't always mean to say that the lowest angle is the best distance, because the best angle is the angle that enables the signal to arrive at the destination we're aiming for. But we don't really have too much control over that, because once we've erected our antenna, it's all predetermined. Now, the vertical antenna is a prime example of that. It gives very low angle radiation. But what perhaps we don't always realise is how effective that low angle radiation is, and in fact whether it's actually going anywhere at all. So I thought I'd do a little bit of investigation and see if I can come up with some facts and figures that may indicate what we actually experience, particularly in a small backyard or back garden. You know, for a long time I've had my reservations about the low angle radiation properties of vertical antennas. There's no doubt that they should provide very good low angle radiation. I'm told that in the textbooks. But there's certain facts that are missed out on many textbooks, and also in more recent times modelling software seems to ignore one very, very important fact. A fact that's so important that it could mean that a lot of this modelling software is not really telling us the truth. Well, we all like to know the truth, don't we? And as ham radio operators, it's nice to ferret around and see if we can find out a bit more about what our antennas are really doing. So that's the purpose of this short video, really, to have a look at the low angle properties of vertical antennas and how perhaps we're missing something which we should know about. Now I'm going to put up on the screen a picture of the radiation pattern, the vertical radiation pattern of a quarter wave vertical, ground mounted. And as you can see, it's what we'd expect. It's got some nice low angle radiation. The point of maximum radiation is 26 degrees, which seems to be about right. I do notice that the shape of the lobe seems to vary from one bit of software to another, and certainly from the software to the textbooks, but it's not radical. So there we have it. We've got a vertical radiator, and we've got a decent lowish angle radiation pattern, and we've got some reasonable radiation at lower angles than that, because 26 is the peak, but we can go down much lower. And doesn't seem much wrong with that, does it? But then, if you look at the RSGB Handbook 1969, and I chose that because I happen to have a copy of it, it actually shows something rather interesting. Apart from the fact that my photo appears on the top right hand side of the cover, but that was a long time ago. Now, if you look at the screen, you'll see an image taken from the 1969 handbook. It's not a quarter wave, it's a half-wave vertical antenna, 1/8 above the ground. But the interesting thing is here, if you look at that shaded portion is cancellation caused by the Brewster reflection. You'll see that there is nothing below 10 degrees or 11 degrees. Everything below that is cancelled out by the Brewster reflection, something which never seems to appear in modelling software. Before we go any further, let me explain something. I've had verticals over the whole of my ham radio life, the last 60 plus years. I've usually had a vertical in the garden, very often a ground mounted vertical, and I think it stemmed originally from the fact that as a youngster, newly licensed, I was told that vertical antennas were great for DX, and I've worked a lot of DX on verticals, and When I've had a small garden, I've used a vertical and it's been fine. But I've always noticed that there's not the difference between a vertical and a horizontal antenna that I expected. Now, I've quite frequently put up dipole antennas, and they've usually been fairly low, around about 20-25 feet above the ground. And when I've been trying to work DX, I've switched between one and the other. And I've always been surprised that the vertical antenna doesn't seem to be any better than the horizontal antenna. And very often the horizontal antenna seems to be a bit better. Now, when I'm talking about DX, I'm talking about long haul DX, the west coast of America, Australia, New Zealand. Very rarely is the vertical better than the horizontal antenna. And that's always mystified me, and I've never really understood it. I've put it down to propagation, put it down to the fact that my dipole perhaps is pointing in a better direction, but none of these theories really stack up. There's got to be something else. And this is something else that recently I've been looking at, hence this video. Now, the Brewster angle, as it's called, it's been around for a long time. Basically, it relates to light, the transmission of light, reflection of light and images and so forth. And because radio waves are not unlike light waves in the way that they travel and are reflected and bent and so forth, the Brewster angle has been applied to the transmission of radio waves from antennas. And in fact, it's something called PBA, pseudo-Brewster angle. And it basically explains how the ground reflection from the radio waves that hit the ground actually bounce back and cancel out low-angle radiation. Now, although it's been known for a long time, it's not often mentioned. And as I say, I first saw it in the 1969 RSGB handbook. It's appeared in more recent versions of the ARRL antenna book, but it seems to have disappeared when it comes to antenna modelling. Now, the fact that it's disappeared in antenna modelling doesn't actually mean it doesn't exist. It means that it's not taken into account. And it's a bit worrying, really, because you see quite a lot of examples of the vertical radiation patterns of antennas, particularly vertical antennas, and basically what it means is that what you're seeing is not actually what is happening in real life, and that's a bit worrying, isn't it? The Brewster angle is basically the angle at which no interference takes place. It's an angle where the reflections from the ground don't have any effect at all, but it's below that angle where the ground reflections do have a major part. And there's an interesting paper being written by W4RNL, and I'll go through bits of that in a minute. But basically it explains how the Brewster angle, Brewster reflection, or call it what you like, PBA, actually cancels out low angle radiation. Now, the Brewster angle is affected by two factors. One, the frequency of operation, and two, the type of ground beneath it. And surprise, surprise, the worse the ground, the greater the amount of cancellation that takes place, and the higher the angle is. So if we take seawater, the Brewster angle is very low, and therefore it doesn't have nearly so much effect as the ground in your backyard or your back garden. So let's go through this paper by W4RN, or at least go take bits of it out so that it just explains what is likely to happen in your backyard and why antenna modelling at this particular aspect of modelling is so misleading. This is the paper that I'm talking about, written by W4RNL, and I'll put a link below this video so you can actually look at the paper yourself. It's quite comprehensive, and it's interesting reading. Now, he opens by saying that the Brewster angle is never shown on modelling software, not the sort of software that you're likely to come across. So it's missing. Now I'm going to put up on the screen this picture here, which basically is a 7 megahertz ground mounted vertical with 64 radials, and it shows the typical radiation pattern, and also it shows the Brewster angle. So let me show you that on the screen now. This is the modelled antenna, a quarter-wave vertical ground mounted, operating at 7 megahertz with 64 ground radials, so very comprehensive ground radials. And the overall outline, you can see the radiation pattern, the vertical radiation pattern, and you can also see the 3 dB points. But missing from this is the Brewster angle, which has been drawn in. I'll just show it to you here. See that line there? That's the Brewster angle, which is around about, what, 14, looks like about 14 degrees on this illustration. Now the article makes the point that everything below the Brewster angle rapidly decreases in signal strength at the far field. So in other words, below the Brewster angle we can expect quite rapid deterioration of the radiation pattern. It also makes the point that the two things that affect the Brewster angle is the earth quality, the earth below the antenna, and the frequency. And also that you cannot change the angle by changing the antenna design. And also, as you raise the antenna above the ground, the Brewster angle still remains the same. Now the modelling software does either consciously or subconsciously acknowledge the phase cancellation of the Brewster reflection, because if we look at this picture here, we see what the radiation pattern would be over a perfect Earth. Of course it doesn't exist. So the classic radiation pattern which we see on modelling software does acknowledge the Brewster effect, but it doesn't actually take into account how the Brewster effect can quite rapidly reduce radiation below the Brewster angle. Now if we go back to the paper that I've been talking about, the article I've been talking about, there's a very interesting diagram there which actually shows the effect that the Brewster angle has dependent on the quality of the ground and the frequency of the radiation, frequency of the signal. And it basically indicates that for all practical purposes, if you've got average ground, which I think most of us probably have, if you've got an average ground, then it's from 7 megahertz upwards that the Brewster angle is fairly important, and in fact it flattens out at around about 15 degrees. So you can say that anything above 7 or 8 megahertz, the Brewster angle probably in your garden or backyard is going to have, the Brewster angle is going to be about 15 degrees. Lower frequencies, the Brewster angle comes down, so it's not so severe in terms of reducing the low angle radiation. It would be nice to actually have some examples to see what the actual loss is, but unfortunately there are very few examples. There are the mathematical formulas to work it out. They're highly complex and way beyond my capability. But I have found an example which perhaps demonstrates how rapidly the fall off is. And it's from a paper by N6MW. Now this paper actually was applying the Brewster angle to a 160 metre vertical antenna. Now we know from what we said earlier that the Brewster angle is always much lower on the low frequency bands than on the higher frequency bands, which means to say that the drop-off is at a much lower angle. Let's take a sort of basic rule of thumb. We know that the Brewster angle is always well below the angle of maximum radiation, and in the example which I gave earlier, the radiation angle was around about 26 or 30 degrees, and the Brewster angle was around about 15 degrees, and that was on 7 megahertz. Now, this particular example I've got is on the 160 metre band, and the angle of maximum radiation is 13 degrees. and the Brewster angle is actually 3.5 degrees. Now I'm going to put up on the screen the graph, if you like, to show how steep the drop off is below, or as you approach the Brewster angle and below the Brewster angle. So let's have a look at this particular example of the 160 metre vertical antenna. On the screen here is a graph. The top horizontal line represents the angle of radiation, and the vertical line on the right represents the dB loss. Now, on this particular example, it's a 160 metre vertical antenna. The maximum radiation angle is approximately 13 degrees, and the Brewster angle, which is not actually shown, is 3.5 degrees. So if you look at the 3.5 degree point along the horizontal line, you'll see that there's already a significant drop-off, and the drop-off beyond the 3.5 degree is very, very rapid indeed. Now, let's then imagine that we've got our 7 megahertz antenna where we've got a maximum radiation of 26 degrees and we've got a Brewster angle of 15 degrees. And you can see from the demonstration of this graph that at the 15 degree Brewster angle point on the 7 megahertz vertical, there would already be a significant drop-off, and the drop-off beyond that would be very, very rapid indeed. So it would certainly impinge heavily on the 10 degree angle, and the 5 degree angle would have virtually no far-field radiation at all. It does mean to say that if the Brewster angle is at 15 degrees on bands from 7 megahertz upwards, it needs to be taken into account, and the problem is that the modelling software doesn't take this into account. Therefore, it means to say that if you look at your low angle radiation on your modelling software, almost certainly it won't tell you the truth. It's very unlikely to have anything around about 5 degrees. 10 degrees is probably where your angular radiation starts to be noticeable at the far field. In other words, if you've got a decent antenna system up and you've got average ground, you probably are going to get some radiation at 10 degrees, but that won't be the optimum. The optimum will be around about 26 degrees. So forget 5 degrees because it's not going to happen. And also, of course, we have the practical aspect that if you laid on the ground and looked up at an angle at 5 degrees, you wouldn't see any say daylight. You wouldn't see any sky at all, because you're going to have buildings in the way, and not only one building, but multitude of buildings in the way. And the performance of your antenna is not only dependent on the building next door that gets in the way, it's also dependent on the buildings and buildings and buildings beyond that. So for all practical purposes, 10 degrees is more realistic, and even 10 degrees is probably going to be quite severely attenuated in many locations. So what is the point of all this? Well, the point of all this really is to explain that don't be disappointed if you don't get the results you expected from your ground-mounted vertical antenna. We now know that there's an invisible item that's not shown in the modelling software, which is the Brewster angle, which is quite important and will have a major effect on low angle radiation. There's no easy way of actually evaluating how your vertical antenna is going to work in your particular location, but it's a fair bet that you're not going to get anything below 10 degrees, and you'll probably be quite fortunate if you get anything below about 15 degrees if you take into account the urban situation that many of us have to operate from. So take heart, because for a lot of DX operation we don't need ultra low angle radiation anyway. A lot of DX contacts are made through multi-hop transmissions, and I covered that in a video fairly recently covering shortwave propagation. And you can work DX with fairly reasonable angles of radiation around about 25-30 degrees very often. That's all you need. You don't need ultra low angle radiation unless you're a member of the Flat Earth Society and believe in flat Earth. Perhaps these modelling programs, when they're illustrated, they should really come with a health warning, particularly when the discussion is about angles of radiation. Perhaps they should come with a health warning. QST have acknowledged that the Brewster angle not only exists but is important, and that the RSGB in their handbook back in the late 1960s also acknowledged the Brewster angle and how important it was. So with this modelling software, perhaps we should have a health warning. There we are. In the meantime, thanks for watching this video. I hope it's been informative. I've tried to sort of make this fairly informative, but do read this paper because it's very interesting. And as I say, there's a link below this video. In the meantime, enjoy your ham radio, take care, and I look forward to seeing you in the next video. Bye for now.